Good morning, everybody. So now we go more in detail on how to work with spectral data on Mercury. We focus our attention on two instruments on board messenger mission. So the first one is the Mercury dual imaging system, and the other one is the visible infrared spectrometer. Okay, so messenger had on board a spectrometer, masks, so the Mercury atmosphere and surface composition spectrometer. This instrument was divided in two. So we had an ultraviolet and visible spectrometer that was more focused on the exosphere analysis, and the visible and infrared spectrometer, which was devoted to the study of the surface. This spectrometer had two detectors, one for the visible channel between 200 and about 1000 nanometer, and the other one for the infrared between 850 and 1040 nanometer. Then we had a camera which includes two different cameras. A wide-angle camera was equipped with a filter wheel with 12 filters. Really, the filter we use for the analysis are 11. One is for internal calibration and of the camera, and the range of wavelength covered is in the infrared range. So is the typical range for multispectral cameras, so between about 400 and 1000 nanometer. Then we have also a narrow angle camera, which was centered at about 750 nanometer, and the data of the narrow angle camera are the data which was used for the geological analysis, and are the data you will analyze this afternoon. But now we will focus more on the multispectral and hyperspectral data. I would just want to show you here an example on what are the data we will see today. So on the left, we have the data from the multispectral camera. So you see spectral in the visible range with just a few reflectances for different wavelengths. So we have about from 8 to 11 point. Then on the right, you see a typical spectrum of the visible and infrared spectrometer. You see in the A panel the average spectral Mercury, and then in the B panel some other spectra of other regions. So we see better later in detail. Let's start with the with the wide angle camera data. So we have global mosaics at different wavelengths for this data set. Here I just show you the global mosaics at 750 nanometer. But one of the main approach you can use to analyze spectral differences on a surface is, for example, to use RGB color combination. So you can put all the filter and produce some different color combinations. So I show you just an example. So you can try with different kind of combination, but here I want to show you Mercury in true color. So I use the RGB wavelength more close to the true color wavelength, just to show you how Mercury will appear with our eyes. So you see here, just looking this RGB, that we have different color of Mercury surface. So, for example, you see that in the northern areas and also in other regions, we have terrain that are more redder than other. So you see other terrain that are more darker with so they have lower reflectance and show more bluer color. You have also bright material, so you see, looking this image, that you have variegated colors on Mercury, but these colors are not just color. They indicate something. So they indicate, for example, that for this different color combination, you can have also spectral variation. So, for example, you see in the red plane in the circles that you see red, but they are red because you see an increasing of the reflectance, increasing the wavelength. So it has a specific spectral meaning. And the same for the blue plane, which show an opposite behavior compared with the red plane you see here. But if we choose other combination and not, for example, just this true color, but we use in the RGB other kind of parameters, for example, the principal component and spectral ratio, we can better emphasize these color variations. So this is the famous enhanced mosaics of Mercury. And this is one of the main use from the messenger team to analyze the Mercury surface. And in this case, using this kind of RGB combination, you can very well emphasize what are the spectral variation on Mercury. So you see, you can also identify different terrains. So you see that here the northern smooth plains appear in yellow color, yellow-orange color, that are very different from the blue, low reflectance blue plane. You can also see that you have a very dark blue regions, and these are the low reflectance material of Mercury. Then you also can see other areas, very small areas with orange color, and these are the faculae which are associated with pyroclastic deposits. So you see, you can just looking this and simple RGB combination, how much information you can have from the spectral point of view, and so you can identify different terrain which has different spectral behavior each other. Just a few examples, a close-up, for example, of Caloris Basin, the largest basin on Mercury, which show smooth planes inside, but also other kind of feature. For example, pyroclastic deposits you see in dark orange, and other craters in the floor. Then another interesting region is the region of Rachmaninoff crater and Natal Facula. You see this region in the previous presentation, and here you see, for example, in the Rachmaninoff floor, a very blue material, but this material is not like the other blue, the material of the blue plane, because you see a more intense color. And this color indicates a different kind of material you see here. In this case, the dark material is associated with the material coming from the underlying layer of the surface, and it can be representative of the Mercury primary crust. While the Natari Facula, you see in the northeastern part of this crater, show a very large facula, is the brightest feature on Mercury, and you see also the large vent here, but you can see also other kind of similar feature in this region. For example, another vent on the left of Natari with a less bright facula, but also you see other deposits on Rachmaninoff floor. From this kind of color combination, so of RGB map, messenger team identify different terrains on Mercury, which are classified on the left. So they started from the map in panel A, and they derive on panel B the different spectral units terrains. So we have high reflectance plane in yellow, light yellow, which correspond mainly on the smooth planes. Then we have an intermediate plane in dark yellow, the low reflectance blue plane, which are in light blue, and then we have the low reflectance material in dark blue, similar to those I show you in the previous slide, so like those in Rachmaninoff crater. On the top left, you see the spectra of each different terrain identified here. So you see that the high reflectance plane are characterized by highest reflectance, but also steeper spectral slope. So you see that intermediate planes have a similar behavior, but with a shallower spectral slope with respect to the high reflectance plane. And then you have that the blue and reflectance material plane are distinct from the other two because they show a lower reflectance, but also a shallower spectral slope. So you can just looking this RGB combination, you can identify what are the spectral differences of different terrains on Mercury. Not only on Mercury, you can do this for sure for also for other body. You can do a similar work also for using the visible and infrared spectrometer. This is an example of RGB combination considering the spectrometer on board messenger. This is the global map, And also in this case, this kind of color combination have been used to emphasize different kind of terrain. I want to show you just a close-up of a particular areas, the Tolstoy-Beethoven area. And here, the different color represents different kind of feature. For example, the feature in orange or in red are mainly associated with pyroclastic deposits, while the intermediate plane are in purple, and you have in blue cyan the low reflectance material, but you also see yellow color, and this is typical of bright material. So you see that also in this case, you can use this kind of analysis to identify different terrains with different spectral properties. But what is the spectral behavior in this case? Also in this case, we can identify different spectral showing looking at the different features. So you see, for example, in panel A, the Mercury average spectrum. So you put together all the spectra and you see this kind of quite flat and red spectra. Then in the B panel, you see the spectral representative of different kind of terrain or feature. For example, you have in yellow typical spectra of fresh material. You have hollows in green, pyroclastic deposits in red, smooth planes in black, and low reflectance material in blue. You see also in this case that looking the RGB map, you can identify different terrain units, and then each one has a particular spectral behavior. So they are related to each other. And also in this case, you see that the highest reflectance and feature are the fresh crater material as expected. Then you have hollows. And you see also in this case that these spectra are quite flat if you look in the visible and infrared part of the spectrum, but you have a sort of downturn in the part of the spectrum closer to UV. So in this case, you can characterize the spectral behavior of this kind of feature, and you can also define parameters that can be useful to identify this kind of feature in the surface. So you can then calculate this and apply to the surface, and then identify where this kind of feature can be distributed in the surface. Another way to better emphasize the spectral behavior of different areas, different terrains, is shown in the C panel. And here you have a normalized spectra. So you just divided the spectra in, the spectra in panel B. For the average spectrum, you see shown in panel A. And in this case, you remove the reflectance effect, and you can better see the real spectral variation, which are mainly based on, in this case, spectral slopes. So you see better the very high downturn in the UV of the yellow spectra with respect to the others, which are very quite flat, for example, in the case of smooth planes and low reflectance material. So this tells us, for example, that smooth planes are more similar to the average spectrum of Mercury, while low reflectance material here tell you that you have a lower reflectance with respect to the average spectrum, and but from the spectral point of view, you don't see particular differences in terms of spectral slopes. Another kind of analysis, another kind of approach you can consider to extract information from the spectral data is to define spectral parameters. Spectral parameters depend on the characteristic of the spectrum. There is not only one way to define spectral parameters, but the best way to define spectral parameters is to look the properties of your spectrum and then decide what are the best ones you can consider. On the left, I show you some spectra. These are spectra from the moon, and I wanted to show you this spectra because you don't have only spectral slope variation as you see in the previous slides, but here you have also absorption bands. When you have absorption bands, you can better define the mineralogy of surface because each absorption band is related to a mineral, and then you can associate the mineral to the spectra of your surface, and then you can tell or try to tell what are the phases present. The main spectral parameter that in general we use to define the mineralogy and the spectral properties of a surface are mainly these three. So the band centers. Band centers are important because you can this parameter give you information on the composition and on the mineralogical phases present. So each, as I told you, each minerals has particular absorption features centered at particular wavelengths, so we can compare this with our surface and then understand if we have what are the minerals present. We have also the band depth that is important because this kind of parameter is really related on mineralogical abundances of the phases present, but also on grain size variation and also on the present on opaque material. Generally, the band depth can varies with the grain size variation. So if we have, for example, the same mineral measured at different grain sizes, we see in some cases an important variation in the band depth. Opaque material, when present, have also the effect to reduce the depth of the band. And these three effects are strictly related to each other. So it's not easy to discriminate what are the main contribute to the band depth just using this parameter. So it's better to associate to the band depth also other parameter, for example, reflectance or models, for example. The spectral slopes are instead important because they give us information of the terrain maturity, the composition, but also the grain size. And this parameter is the main parameter we use for Mercury, because we don't have absorption band, so we cannot use the other two, but we have just to see and characterize our spectra looking the spectral slope variation. We see that we have a red spectral slope when we have steep slopes. So in this case, we have, for example, this kind of spectral slope are typical of mature terrains. And then terrains more affected by space weathering, you see particular red spectral slope on Mercury, but also on the Moon. They can be related with composition. For example, if you see the spectra of the pyroclastic deposits and the smooth plains, there are smooth plains, you have red slope, so steep slope, but in this case they are not related with the maturity of the terrain, because in this case we have more young terrain with respect to other on Mercury. So in this case, related to the material.
Less than 5 minutes.
Okay, then you have also shallower blue spectral slope, and also in this case they are typical of unweathered material, but also composition, for example, dark terrain and also ices, not our case, show shallower spectral slope. These are the typical spectral slope you can use for Mercury. So you can use the spectral slope close to the UV range, so between 400 and 560 nanometer, and is useful to define the presence of opaque material, but also volcanic material. You can also have the spectral slope in the final part of the spectrum, so between 700 and 1000 nanometer. In this case, it's useful to see if you have some inflection here, to see if you can have the presence of the 1 micron band typical of the iron absorption, and the global slope to see the maturity of the terrain. This is just an example of a quadrangle of Mercury where you can see the spectral slope variation. You have the reflectance in the A panel, the global slope in the B panel, and the spectral slope in the UV range in the C panel, while you have the slope close to the infrared range. In the D panel, you see the variation, and you see that dark material and young material show a lower value of this slope, but if you associate this with the reflectance, you can better distinguish which is one or the other. So in some way, you have to combine all the parameters to derive the information. Just a close-up of the Rachmaninoff and Natal facula, so you can better see which are the differences in these areas. Then I want to show you something about hollows, because these features are the one which show larger variability on Mercury, and for the first time with the wide angle camera data, some absorption has been observed in some particular hollows. You see the spectra on the left, and you see an absorption close to 600 nanometer. This absorption can be associated to sulfides, magnesium or calcium sulfides, or a combination of these two. Also in this case, you see some typical spectrum of different regions, and these are spectra from the visible and infrared spectrometer. So you see the comparison between low reflectance material, faculae, northern smooth plains, and hollows. And another kind of analysis you can do is putting together in a plot different parameters to see if you have a correlation, and if you can identify cluster which can clearly identify the feature you want to analyze. And so in this case, for example, you see in the reflectance at 750 nanometer with a visible spectral slope, which identify different cluster for the different hollows and terrains, and a similar plot you see on the bottom. Another work, another kind of analysis you can see is also define specific spectral parameters for hollows in this case, which is, for example, the main parameter is the downturn in the UV range. Then you can divide in different groups the value you find for different hollows, and so you can define different type of hollows based on this parameter. This is another kind of analysis you can do. You can do for hollows for sure, but also for other terrains. Is just an example. And also putting together in a same plot the reflectance, for example, and this UV downturn, you can identify different kind of hollows. So you can see in this plot these four type of hollows. For example, the blue one, the first type, is characterized by low value of this UV downturn parameter, and then the red one is the one which show larger value of the reflectance, which is associated with higher value of this of the downturn parameter. Another kind of things you can do is also not only look the spectral variability, the spectral properties, but it's important also to associate the spectral variability to the geological feature you are observing. So if you see, if you put this behavior, this hollows in the global map of Mercury, so you can see where these hollows are located, for example, and so you can also identify what is the distribution, and if some type of hollows are, for example, associated to a particular crater or particular geological feature. And this is also an important analysis you can do. So the final analysis you can do is integrate the spectral and the geological information. So I conclude with this, and thanks for your attention.